Okay. So let's get started with our first task today. We're going to do one-dimensional problems. 1D problems. So we're starting in one dimension, as I was saying, because we want to make sure that we understand the essential ideas of the class, of how it all fits together. And to do away with the other two dimensions makes our life much easier. And also, it allows us to deal with a very important mode of loading for structural mechanics, which is the case in which you have essentially a straight bar. So you're going to have a straight bar, something that looks like that. And the cross-section can be changing as long as it changes slowly. But the bar is straight. So you have a section of the bar here. Let's call this section A. And you're going to have on the other side the same cross-section. And this is going to be section B. So the bar is straight. And along this straight bar, we're going to have forces acting on the bar. And also the forces. So the force that acts at B, I'm going to call it FB to remind myself that the force acts at point B. And the force that acts at A, I'm going to call it FA to remind myself that the force acts at point A. So in the 1D problems, everything will happen along one direction. And that direction is going to be our coordinate axis, x. And the forces act along the axis of the one-dimensional structure. And so these 1D problems are called problems in axial loading. And that's what we're going to deal with today. OK, so because everything is in 1D, then the description of the forces is also very simple. Because essentially, your forces, although they are vectorial quantities, you see we put the arrow on top to remember forces are vectors, they only have one component, which is the x Cartesian component. So in one dimension, my force FB is going to be simply equal to Fxb acting along the x-axis. So let's put a unit vector I along the x-axis. So FB is going to be Fxb multiplied by the unit vector I along the x-axis. As simple as that. Now, depending if FB or FA point along the x direction or against the x direction, the way I see this is I see the sign of Fxb. So if Fxb is positive, so it means that FB points along the same direction as the x-axis. If Fxb is negative, then it means that FB points in the direction opposite to the x-axis. Right? So 1D, force, Cartesian component times unit vector in the direction of the coordinate system. And the Cartesian component is positive or negative, depending on the force goes with the axis or against the axis. Of course, FB is also going to have a magnitude. So the magnitude of FB, in 201, we just simply call it FB without the arrow on top. Of course, the magnitude is like the length of the vector is always positive, right? So the magnitude of the vector we indicate without the arrow on top. And this is the same as the absolute value of your x component. OK? So problems in axial loading look like this. And how do we deal with equilibrium for structures in axial loading? So equilibrium becomes really simple. So what are the conditions for equilibrium of this bar? When is this bar going to be in equilibrium? How do we check equilibrium? What do we do? What do you think? Sum of the forces is equal to 0. That's exactly right. So we do sum of the forces is equal to 0. And because we are only in the x direction, which components of forces do we need to check? X. I don't want to insult your intelligence. I'm sorry. Sum of the forces x must be 0. So what this means is that the Fxa plus Fxb must be equal to 0, from which we see simply that Fxa must be equal and opposite to Fxb if the structure is in equilibrium, which is what we kind of throw over here. To have Fxa equal to minus Fxb, it means that if Fb points that way, Fa got to point the other way. And they must be equal in magnitude for this bar to not start flying to Timbuktu. Correct? Good enough. All right. So you see how everything gets nice and simple in 1D. One thing that I should remind you of, let me put it up here, is units. Forces have units. So in 201, we will mainly use SI units, right? SI units are the preferred father of 201. SI, which means that the forces are in newtons, okay? Newtons. I know that we also use pound forces and other kind of things like this in this country, but let's use SI units. Maybe I'll give you 1 or 2 problems with like pounds and inches and feet and all these other kind of stuff that messes me up, okay? Maybe you know it better than I do. Okay, so equilibrium. What do we do with equilibrium? The first thing that we want to do with equilibrium is we want to use equilibrium to find the reactions at the supports of the structure. So this is a very simple proposition. Essentially, imagine that you have a bar sitting here attached to a wall. Now, our wall is going to be a main character of 201. Essentially, every time that I want to say that the structure is fixed to something, I'm going to draw a wall. A wall is something that is there. It grabs the structure and prevents it from moving. At the wall, the structure cannot rotate. Essentially, the wall does everything that is necessary to do in order to take this section here of the structure and just encastre it there and prevent it from going anywhere. Okay, so if I load the structure, the wall is going to give any force and any torque and any moments. We're not doing torques and moments yet, but it's going to do anything to prevent both translation and rotation. Okay, in 1D, the wall attached to the structure is going to have a very easy job. So just to fix up the ideas, let's say that I have a bar. I'm going to make it of constant cross-section, but that's not necessary. But let's just make it like this for now. And so this is our bar AB. And at this end of the bar, I'm going to apply a force, FB. Now, just because we want to put some numbers, let's say that FB, the magnitude of FB is 1 kilonewtons. And the first thing that we want to figure out is what is the reaction force at the support. So for reaction, we always use the letter R. And as I was saying, because the only thing acting on this bar is a force in this direction, and let's put our x-axis. So the x-axis is in this direction, and let's put x equals 0 at the wall. Doesn't matter for now, but let's put an origin for the x-axis. So everything happens along this direction. And the only thing that is acting on the bar is a force in this direction. So if I look at the reaction of the support, and let's call it RA because it's the reaction at point A of the support, the reaction at A, what components is going to have? What do we need? Do we need Y, Z? No, none of that. So the only thing that we need is really Rxa. So Ra is going to be Rxa times the unit vector I. Now, you see this Rxa? This is our only unknown in this problem. So the way we find unknown forces in 201 is we do a free body diagram. So when you do a free body diagram, you free the part of the structure that you are interested in from the rest of the structure. You expose what was happening in the point where you cut the structure away, and you put that part of the structure in equilibrium, and by doing that, you figure out what your unknown was, okay? So we want to figure out what happens at the wall. So what we do, the first thing that we do a free-body diagram where we totally get rid of the wall goes, and we are left with just a bar, and the bar has the force at BFB. We don't throw that out. When you do a free-body diagram and you get rid of the wall, do not get rid of the forces. The forces stay. They're there to stay. If you draw a part of the structure which has a force, the force stay in the structure. And now here we get rid of the wall. But we cannot just simply get rid of the wall without doing anything else, because the wall was doing something on this bar, right? The wall was attached to the bar. It was doing something to the bar. It was giving a reaction. So we need to put here the reaction on the wall. So now this is very important. The way that we put in unknown quantities in our free body diagram in 201, we do not draw them the way we intuitively think they're going to go, okay? I see this, I can already see, I mean, this guy is going to pull that way, right? What am I doing here? This is the simplest example you can do. So now you can kind of see it. I don't want you to do these kind of things. I want you to draw the unknown quantities in the way they would act if they were positive according to their convention. Is that clear? So if RXA were positive, what this means is that it would go that way. I draw it that way. That's the direction of x. A positive RXA would go this way. RXA is my unknown. So in 201, the unknown, we always draw in the way they would go if they were positive. Okay, that really helps not to get mixed up in more complicated problems. So you do your free body diagram. This is your unknown. You drew it positive. And then the second step that you do, you impose equilibrium. So we do the same thing we did that. We say sum of the forces x is equal to 0, and that's equal to RXA. And now you look at the forces. You look at the forces and you say, if I take this force and I project it along the x-axis, will I get plus the magnitude or minus the magnitude? This goes with x, so it's going to be plus FB. If I had a force here that went that way, say this is a point C and this was FC, if I had also this force here, I would say RXA plus FB minus FC, because FC goes against x. So when I project it in x, I would have minus FC magnitude. Do you see? We good? Let's take it away, because this is way too advanced for the first class. I mean, I want to make your brain explode with these kind of complications yet. Okay, so we get this. And so out of that, you see that I get simply that RXA is equal to minus FB. And the FB, the magnitude of FB, was 1 kilonewton. So RXA is equal to minus 1 kilonewton. The fact that it comes out negative, it means that the real value goes against the x-axis. So the third thing that you do, you always check your answer. So once you have an answer, check it out. Make sure it's correct. Don't forget this step. So to check it out, you just draw the bar, and you draw the things you know. FB points this way. The magnitude is 1 kilonewton. So you put 1 kilonewton this way. RXA is 1 kilonewton negative, so it goes opposite to this. You put it this way. Notice that I do not write minus 1 kilonewton. I took the minus by putting it against the x, right? And then I look at this structure and I say, does that look in equilibrium? Duh, yes it does. Okay? Now I know this looks like overblown waste of time. Believe me, it's not. It's not. If you just learn to do it according to this like turn the crank kind of thing, you're not gonna get messed up with which sign is the unknown, which way it goes. You will know, okay? Okay, so we're gonna do now something very important. Let's see if I have my little high-tech demo. I have it. So are we all done with this? Is this all what we need? The answer is not. So if I take this eraser and I tell you, now we learn everything about equilibrium, you think, in axial loading. I take this eraser, I pull with a force this way, equal force this way. It's in equilibrium. It's not going anywhere. I'm done. Everything I need to know about axial loading is finished. It ain't. It's not finished. It's not finished, and to show you it's not finished, I will use this handy-dandy high-tech demonstration. So if I take this thing and I pull with the force that way, and I pull this little nifty thing with the same force in the opposite direction, this is not going to stay put. See? I'm pulling with equal forces. This thing moves. Something happens. I cannot just pull with equal and opposite forces and nothing happen. At this point, when I try to put equal and opposite forces, what happens is that inside the rubber band, right here, there are no forces. So this side here of the rubber band, I pull it this way, and nothing is pulling back, so it goes. The same way, this part here, inside there is no forces, so it moves. If something accelerates, it means it's not in equilibrium. Only now it's in equilibrium. You see? In order for this deformable body to be in equilibrium, something must be happening inside. There must be inside the structure, a force inside the structure that balances the applied load. Otherwise, deformable structures are not in equilibrium. And every real structure is deformable, right? Rigid is a theoretical simplification. The reality structures are all deformable, and the equilibrium must not just be of the outside forces, but also what happens inside. So there is a force inside the structure, right? That's the one we are interested in. So let's figure out what this force inside the structure is. So what we're going to do now is find another piece of chalk. All right. So we are ready to go a place you have not gone before, inside structure. So you're going to find internal resultants of a structure in axial loading. So the idea that you have is the same idea that you have here. Is the same structure as this one, but now you're asking yourself, what must be going on inside the structure? So here is the structure. Boom, boom. This is my point A. This is my point B. I have FB, and I have FA, which now we know is minus FB. We know that because we did it before in the previous board. So now what we do is we do something which is one of the most important tools in structural mechanics. We cut the structure. We take a pair of scissors, snip, 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 and we make a cut. And what we do after we make a cut is we expose the inside of the structure. And we take only one chunk of the structure. I can take this side or I can take that side. The answer will be the same. So for now, I take this side on this side and say that I cut at some position, it doesn't matter, x bar, if this is my x-axis. I cut at x bar, and now I have only this side here of the structure. I have FB still acting on that side. And you see that there must be something going on inside, because otherwise, this chunk of the bar goes, what is that way? Watertown? I don't know. Another town. But it doesn't stay with us. The reason that it stays with us is because this part here that we got rid of was doing something. It was pulling on it. There was a force inside the structure. Because it's acting along the axis of the structure, we call this force an axial force. We use the symbol curly N. This is an N with a curl to indicate axial forces. And N is our first example in 201 of what we call an internal resultant. Internal resultants are very important in 201 because internal resultants measure what the structure feels inside. Okay? And they have their own convention for signs. So the sign convention for internal resultant N is the following. If you have a bar that is being pulled like that, then N is considered positive. And this is called intention. If what happens to the bar is that the bar is pushed in like that, then the axial force is considered negative. And that is called compression. Let's put a minus sign here to remember. You see, when I draw this, have I asked myself which way does the x-axis go? Have I asked myself, does the x-axis goes that way, goes that way? I don't care about the way the x-axis go when it comes to the sign of internal resultants. The internal resultants measure what the structure feels. That the structure feels pulled, that the structure feels squished. If it feels pulled, N is positive. If it feels compressed, N is negative. Doesn't matter the way the x goes. Okay? Alrighty. So how do we find the internal resultant? We use equilibrium, the same way as we would use equilibrium to find anything else in 201. So we already have a free body diagram. We have an x-axis, so we find N. So if we want to find the value of N, we find sum of the forces x equal to 0. So now, here is the x-axis, right? I want you to see the way I drew N here. See the way I drew N? I drew it coming out of the surface. Why do I draw it that way, although I do not know what is the sign of N? I draw it that way because N is an unknown. And so I draw it positive according to its own convention. Okay? When you make a cut in the bar, you always draw N coming out of the cut for the structure you're keeping. You're keeping this chunk, N is coming out that way. If I cut and take in this chunk, N, if I look at this part here, will go that way because it will be coming out of the section. Okay? All right. So sum of the forces x equals 0. Now I sum along x. When I sum N along x, is it plus or minus? What is it? Plus. No, minus. Because when I'm projecting on the x-axis, see, this goes opposite. So if I do N dot I get a minus sign. Do you see that? I drew it positive, but when I project it in x, this is a minus N. You see? OK, so minus N, FB is going that way. Oh, I forgot the arrow on top of FB. FB goes that way, so I have plus FB is equal to 0. So out of this, I get that N is equal to FB. You see, the equation tells me that N is positive. I see that N must be positive, must be coming out, because I'm pulling, so N must be pulling too. OK? We're going to do practice on this in your assignment. OK? So are you clear about how we go about this part? Is that clear enough for now? We're going to do so much of these problems. But this is a good start to get us going. All right. So if you want to understand things, if you like vectors and you want to understand this in terms of vectors, you know that a positive RXA goes in the x direction. This kind of convention goes with the fact that the axial force, if you think of the axial force in terms of the vector, is if you have a surface like that, then it will be in positive n coming out. And if you think of n in a vector form, then n will be magnitude of n times the unit vector coming out. Okay, so that's what this convention comes in. But for practical purposes for this class, all what I want you to understand is that when you make a free body diagram, expose an internal force, and you see that you have to calculate the internal force, you put your n coming out of your cut section. That's it. And things are going to be good. Okay. All right. So we're going to do some examples and problems in your homework in which you're going to have bars in which you're going to have more than one force. Say I have a bar with a force this way, and then I may have a force this way, and then I have a force this way, and a force this way. And what we ask you to do is to give me the n at different locations. I may want to have the n at this section here. So what you do is you take this part, you expose n, you put this part in equilibrium, and you calculate what n is supposed to be. Okay? There is an example in your stellar side that is there is a worked out example that explains how to calculate the n in this kind of simple problems. I want you to work it out for your homework and be ready for Thursday, because we're going to do a lot more on this. So let's move on to the next part. And by the way, if I want n at every location along the bar, so this, if this is an x-axis, and I want the whole n as a function of x, because you see here n changes as I move along the bar, right? Imagine that you're doing tug of rope, and then you are like one team on this side, and then there is the guy up front, and then the guy behind, and everybody's pulling. The axial force in the rope steps up every time there is an extra person. That's why the rope in the middle has a lot of axial force. And then you come in at the end, you pull a little bit, the guy next to you pulls more, pulls more, pulls more, so the axial force can change inside the rope. And in general, what we want to know if the rope will break or not, we want to figure out how much is the axial force as a function of the position along the bar, the rope, the cable, and so on. So these kind of things are called the axial force diagrams. And we're going to make these up to when you're blue in the face. You're going to make a lot of axial force diagrams. Okay? So let's go one more step.